All right, so I'm going to talk a little bit about p-values. Basically, what are they? How do I compute them? And then when we run through the examples, we'll take a look at the results. We want to make sure we can go ahead and interpret them correctly. So that's what we've got in front of us. I'm going to put the definition up here. It does get asked about during quizzes and exams. It is a very important concept. But it's a probability. It's the probability of finding a test statistic that is at least as extreme as the one found. At least as extreme as the one found. That's an important notion. And I've got to talk a little bit about the notation now. The p-value itself is written with a capital P. So if you see it in literature, big P, that's going to be a p-value. We also have little p, which is the population proportion that appears in H naught and H1 when you write that. And then there's p hat, which you get from your sample. That's that X over N. And it's not always obvious, and your calculator honestly does a bad job of it. But these two are lowercase p's, while the p-value is an uppercase. So if you see them in writing, you don't want to confuse them. There's a lot of P's in this notation. It's unfortunate, but that's just the way it is. And I want to keep this as basic as possible. So I will note that a p-value depends on a couple of things. It depends on the test statistic. This is a very important notion, this test statistic, in developing the p-value. So it means that test statistic. It was at negative 1.625 in that last example. And it depends on the tail of the test. So I've got to take into account the tail, which means I need to look at, interpret the null and the alternative hypothesis, because they play a big role here. So we use the normal CDF to find that area probability. Excuse me, and I use this for the Z distribution only, and that's for population proportions. This is basically 8.2. Now, as you pointed out with your question, we also use TCDF for area and probability for claims about a mean. And you'll see this in 8.3, where you find this guy here in 8.2. So normal CDF versus TCDF. And you'll need to remember the degree of freedom, but I'll let people remember that on their own. So basically, that's how we find the p-value. I've got a couple of notions here that are going to be important as we go through this. For the left tail test, the p-value is the area to the left of the test statistic. That comes to you from your calculator, or it is given in the problem like we looked at tonight. For the right tail test, The test statistic is the area to the right of that test statistic. So it's important, as I say, to take into account the tail of the test, left versus right tail test. So keeping that in mind, the one that is the most involved is the two-tail test. And that was the one we looked at just a few moments ago. In this case, the p-value for the two-tail test is going to be twice the area to either the left or the right. It really depends on whether the t value given to you or the z value is negative or positive. The point is you've got to supply the other side, whichever one is missing. That's why we multiply it by twice that area. And as I say, we like to find the area in one tail, and then we do what? We double it. So it just saves the work a little bit, and that's really how we approach the problem. So let me go ahead and run through a couple of basic examples. I want to go through the keystrokes, and then we can take a look at a couple of other things. I got some more examples over here, and I want to talk about 8.3 also. So suppose we have these two hypotheses. The null hypothesis is about a population proportion P. The actual claim, the value in the claim, does not matter at all for the setup of the problem. It comes into play in calculating the test statistic, but since we've got that here already, we don't even need to worry about the actual claim values. So we have a test statistic of a z equals a negative 2, 1, 2. So that's my test statistic. There we are, test statistic, negative 2, 1, 2. The p-value will comprise just the left-hand side. How do I know it's just the left-hand side? Because we've got a left tail test. So that tells me I just have to look at the area to the left of my test statistic. So that p-value there, this is where I'll use, what's the program? The program is, in this case, for the z distribution, normal CDF. That's the tool we'll use. So let me highlight that too, because I like my colors. And let me switch over to the calculator. And we'll see what's what. There's a calculator. So normal CDF, I'm going to use in this case, the z distribution, because that's the z-score I have. The lower bound, I will use negative 10 raised to the 9th. I think that's easiest for most people. I could actually use the value that's already in there, but I think people understand this maybe just a little bit better. Enter that. The upper bound is a negative 2.12. The z distribution is 0. Standard deviation is 1. I can go ahead and paste that in and hit enter. And there's my p-value, a negative 0.1700, 3 significant digits. I go to the first non-zero digit, do my counting, 1, 2, 3. I have to look one more out to the 4th. So the 0 makes this 0 stay 0. So 0.0170. Let me stop my sharing from the screen there and note that that's what I've got here. We have our p-value of negative 0.1700. So there's our p-value. In It's relatively straightforward to find, provided you take into account the appropriate alternative hypothesis. Here's another one. This is the two-tail example. Again, I've just given us the t, or in this case, the z-score, the test statistic, and we've got the hypotheses all set up and ready to go. And as I say, the very important part here is the alternative. It's this little guy here that tells me down here, I'm going to be looking at the left tail and the right tail. Whatever I have, I'm going to multiply it by 2. Now you can do a couple of things here. If you're more comfortable using a left tail than the right tail for whatever reason, you can do that. Your p-value, your z-score is symmetric about 0. So if you wanted to use this guy here and find that left area, that would be just fine. I tend to go with what I've been given, so that's what I'm going to use here. I need to remember it's the z distribution with the mean of 0 and the standard deviation 1. Normal CDF. Lower bound, 1.87. Upper bound, 10 raised to the 9th. Mean 0, standard deviation is 1. I'll paste that into my function. I'm ready to go. And I get a 0.030741 and change. 1, 2, 3. 4 tells me 7 stays 7. So I've got to take that. And by the way, I usually use the rounded values when I calculate these. So 2 times 0.0. Boy, that was hard to do. I'm writing it down over there in messy fashion. So I'm going to go 2 times 0.0307. And I should have a p-value of 0.0614. A way to do this without having to multiply this by 2 in a two-step process is, and this honestly is the way most people would do it if they've had a little bit of experience, they'd go 2 times, then they would run and get the distribution function, plug everything in, and let the calculator take care of the multiplication. And there's that 0.06148. See, when I do it like this, I get a slightly different number. I get a 0.0615 if I multiply it by that. Most students use the rounded version, but I've got to be careful when I write these kinds of questions that people know what to do when doing the rounding. So there we go. Questions? And let me be very clear. Let me just run through the interpretation one last time. Here we have a claim. The null hypothesis, p equals 63%. The alternative p is greater than 63%. I gave us all the numbers on this one here. I've got a right tail test. So I've got my test statistic here, and I've got the p-value here. In fact, if I come over to my calculator, let me do this one last time. Let me share Mr. Calculator. if I take over here to stat and to test, then I find my one prop z-test. The null hypothesis was p equals 0.63, 63%. We had a value of 69 for x and 100 for n. We have a right tail test. I said a right tail test. And now I can go ahead and calculate this. You can see my test statistic comes up right here, 1.243. And we've got the p-value, 0.1069 and change. So my calculator, when I do a test, is going to give me a test statistic and a p-value every single time. I even have my sample detail. So interpreting it is really where it's all at. So I've got the p-value, I've got my hypothesis there, the area, the shaded area right here, that is the 0.107. So that's the way that guy comes down. I really want to make it solid that people understand that a p-value is an area. It's an area based on test detail and claim detail. All right, I'm going to stop the recording at that point. Thank you.